Let us solve a numerical example based on the equation of continuity which we have seen in our previous lecture. Let us say that we are given a sphere and the radius of this sphere is R2. This is R2, and let us also assume that it is given that up to R1 initially it had a uniform spherical charge density with charge density equal to rho naught. This is air, and this sphere is made of a material which is having conductivity sigma and permittivity epsilon. So these three conditions are given. Now, since we have seen in our previous lecture that the charge density is going to follow this law, rho is equal to rho naught E minus T by tau, where tau was given as the relaxation time constant rho epsilon, or rho is equal to rho naught E minus T over rho epsilon. This is resistivity, so we should not get confused with resistivity and charge density. Of course, I should have used different signs for resistivity and the charge density, but we should not get confused now because these are standard sign conventions only. Now, as you can see that this charge density is going to follow this law and it is going to decay like this. So the portion which is not having any charge density earlier, it is not going to have any charge density at any point of time. But we also know that the charge density in this region is going to decay gradually with time using this equation, and the charge should come up across or on the surface of this sphere. So the current will flow from this place to this place and carry the charge on the surface. However, the total charge density in this area or volume is not going to change and it is going to remain zero. So we should know the difference between these. That is the current and the charge density. Charge density is not going to change. Of course, current is going to flow from this place to this so that the charge can be taken up to the surface. Now, using Gauss law, we can find the electric field at various locations. So for R greater than R2, we can simply write it electric field as E, it will be in radial direction of course, ER is equal to the total charge enclosed over 4 pi epsilon naught R square, where Q is the total charge given as rho naught into 4 by 3 pi R1 cube. Since I can make a Gaussian surface like this, enclosing this whole sphere, and by symmetry, I can easily use Gauss law and find this electric field. Now, for a point which is lying inside this R1, again I can make a Gaussian surface of radius r, and we already know that for a uniformly charged sphere with volume charge density which is uniform, the electric field inside is given as rho r over 3 epsilon. Now this rho is simply, as I told, will vary according to this equation, so I will put this value as rho naught E minus T by tau r over 3 epsilon. Now I will try to replace this rho naught with Q. So ER for R belonging to 0 to R1 is equal to Q over 4 by 3 pi R1 cube E minus T over tau into R over 3 epsilon. This will get cancelled out and it will remain as Q R E minus T by tau 4 pi epsilon R1 cube. So this is the value of electric field, and you see this electric field is gradually decreasing with time inside a point which is located on a point which is located inside this charged portion of this spherical sphere. Now let us find the field at a point which is lying in the uncharged portion. That is, for a point which is lying somewhere here. Again, I will make a Gaussian surface, and this is R2, this is R, and this is R1. So ER will be simply the charge enclosed by this Gaussian surface. Now this charge enclosed is of course is decaying gradually with time, because inside this charge was gradually decreasing using this equation only. So this charge enclosed is going to decay with time over 4 pi epsilon r square, and this q, as I already told, is simply 4 by 3 pi r1 q rho naught, and the direction is radial, of course. So in this way we have found field in all the three locations. Let me summarize here. E radial is equal to the total charge q over 4 pi epsilon naught r square for r greater than r2, q r e minus t by tau 4 pi epsilon r1 q for 0 smaller than r1, and q e minus t by tau 4 pi epsilon r square for r1 smaller than r2. So we have found electric field in all the locations. Now let us try to find the surface charge density, how it is growing with time. So again I will make this sphere. Now as we know that d1 minus d2 dot a and 2 is equal to the surface charge density. This is the boundary condition, or d1n minus d2n is equal to rho s. So let us say this is surface 2, this is surface 1, this is air, and this is the of course spherical volume with epsilon. So epsilon naught er in media 1 or air minus epsilon er in medium 2 is equal to rho s. Now we will put the value from the previous slide, epsilon, and this er1 is simply q over 4 pi epsilon naught r2 squared, and this value is simply epsilon, and from this slide, q over 4 pi epsilon r2 square e minus t over tau. So from this we can clearly see that this is equal to the surface charge density. So surface charge density is equal to q by 4 pi epsilon naught r2 square. This epsilon is going to get cancelled out. 1 minus e minus t by tau. So you can see that the surface charge density is increasing with time, with the time constant given as this relaxation time constant. So I have proved that the charge is going to come onto the surface, and this is here how it is going to come onto the surface. Now let us try to find the conduction current density in various regions. So conduction current density is given as J is equal to sigma E. Now I have calculated electric field in all the locations, so clearly I can write it, the conduction current density. Now for air, sigma is equal to 0, so the conduction current density is equal to 0 for this R greater than R2, and for R belonging to 0 to R1, that is inside this charged portion of the shell, or the sphere, not shell, it is simply sigma q r over 4 pi epsilon r1 cube e minus t by tau. Similarly, for r1 smaller than r smaller than r2, it will be sigma q e minus t by tau 4 pi epsilon r square. So this is the conduction current density in all the regions. So you see, there is a current, but the total charge density is still zero in the portion which was not charged initially. So in this portion, there is a conduction current, but the total charge density is still zero in this portion. Now, we have seen that the continuity equation is del dot J plus d rho by dot T is equal to 0. Now rho is simply del dot D. So I can write it as del dot J plus dou by dou T of D is equal to 0. So it implies that even if I take that the currents are not steady, then I can say that the divergence of total current, which is conduction current plus this quantity is called as the displacement current density, the total divergence is going to be 0 at any point of time. So what does it mean? It means that the displacement current density dou by dou T of D is equal to minus of the conduction current density, or the displacement current are opposite of the conduction current. Now we can prove this for our example. Now, as you know, D is equal to epsilon E. So I can find the displacement current density JD is equal to D by dou T of D as simply epsilon dou by dou T of E in various locations. So from that, we will find that it is equal to Q R sigma E minus T by tau over 4 pi epsilon R1 cube when 0 is smaller than R is smaller than R1, and of course there will be a minus sign, and for the location when we are between this R1 and R2, we will find it to be sigma q e minus t by tau. This minus sign is to show that it is equal and opposite to that the conduction current density 4 pi epsilon r square and 0 outside the sphere. So we can see that the conduction current density plus the displacement current density is going to be 0 at every point in the sphere, or that is everywhere. And this is of course the other form of equation of continuity. So I hope this example clears your doubt about the displacement current density and the conduction current density, and also about the statement that the charge density remains 0 when it was initially 0 in some portion, even though current is going to flow through it. So I hope this is a quite different example and which resolves your various doubts. So if you find that this lecture helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.